Good afternoon, everyone, and welcome online. My name is Benjamin Debucher, and I'm the head of events content for J Group. Thanks for joining us today. Today's webinar is Growth of Large Format Additive Manufacturing for Tooling Applications with Validate Material Developments. The webinar is organized with Airtech Advanced Materials Group. As you know, traditional tooling methods used in aerospace can be costly and time-consuming, which slows the rapid development that is being required in the industry. Tools that traditionally takes 8 to 12 weeks can be built with additive manufacturing in as little as 3 to 4 weeks, which includes design and any finishing work. Airtech has been extensively testing and validating their materials in use, showing that the materials are more than capable of meeting the demand for production tooling. LFAM tools printed with Airtech Dahltram resin systems can not only achieve high accuracy, vacuum integrity, and rigors of production use, but can also hold up under extended use in the autoclave. Airtech is also developing out-of-autoclave solutions, which integrally heated tools that can both be used in the oven or out of the oven. These out-of-autoclave tooling solutions allow the industry to still use the speed of LFAM and helps keep capital investment down. A further benefit of the Dahltram resin system is their ease of recyclability. Thermoplastic-based tooling solution can easily be recycled once a tool has reached its end of life. This drastically reduces the carbon footprint, helping manufacturers meet key future goals. For those who don't know, Airtech Advanced Materials Group is the largest manufacturer of vacuum bagging and composite tooling materials for prepreg autoclave, resin infusion, and wet layup processes. With nearly 50 years of extrusion experience, Airtech has taken the next step into additive manufacturing with their new large-scale additive manufacturing or 3D printing tooling service for composites. Large-scale tooling in the form of trim fixtures, holding fixtures, and layup molds can be designed, tooled, and built faster without compromised quality. We will be hearing from Zachary Skelton, Senior Technical Support Engineer at Airtech Advanced Material Group. Zach has over 10 years of experience working within the aerospace industry on leading-edge tooling and materials application technologies. Zach has a Bachelor of Science in Aerospace Engineering and a Master's in Business Administration. His experience involves over 10 years with composites fabrication, as well as considerable tooling technology experience. In addition, he has in-depth experience with large format additive manufacturing for numerous current market applications. Zach has been heavily involved in applying Airtech Dahltram recyclable resin system to out-of-autoclave applications. A quick reminder for the audience before we start. We will be, as usual, taking your questions, and we will answer them at the end of the webinar. So you can ask your question in the question tab here at the bottom right of the screen, in the question tab. You can start ask your question from the beginning, and we'll make sure to answer them at the end. As usual, to maximize the experience of the webinar, I recommend to be connected through cable wire rather than Wi-Fi. But in any case, the webinar is being recorded, so you'll be able to view the entire program or review the entire program online later on gccomposites.tv. So let's now discover the opportunities and benefits presented by large format additive manufacturing for tooling applications. Zach, welcome online. It's a pleasure to have with us today. The stage is now yours.
Hey guys, good morning, good afternoon. Thanks, depending on where you're at. Thanks for joining. Thanks for the introduction, Benjamin.
You can go, Zach.
Oh, it's still shows loading on my screen here, but
we can see the presentation. You don't see it?
No, I'm not yet.
Let me reshare it.
There we go.
Okay, perfect.
So as Benjamin noted, we are going to be talking about how Airtech is validating our tooling materials for specific applications. Skip that. Just a little overview. So Benjamin already gave a great overview of Airtech, but we wanted to specifically talk about our large format resin development, just the steps that we take along the way from compounding, printing, mechanical screening, as well as multi-platform validation and working with OEMs for end-use applications. But then also take some time to talk about the elimination of barriers to production use, as well as the functional testing that we're performing. And the use cases and success stories, and then a little bit of the ongoing development and projects that we're working on at the moment. So a little bit about Airtech, really just leveraging our experience. Most of the folks at Airtech came from production environments, composite fabrication history, as well as a lot of historical tooling applications. So leveraging over 50 or nearly 50 years of compounding and extrusion experience, and really just taking the 3D printing, which is essentially just a extruder up on a gantry, leveraging that experience, as well as selecting material specifically knowing the end application. So we do have two locations, one in Luxembourg, which is close to probably most of the folks on this call, but also in Springfield, Tennessee, which is just outside of Nashville. Identical machines, identical footprint, identical team members and capabilities. So in both locations, we have two Thermwood LSAMs. So they are 40 feet by 10 feet by 5 feet build envelopes. Both gantries can cover the complete envelope of the machine. So high deposition rates, we can extrude up to 500 pounds an hour. So tools get built extremely quickly, but then post-printing, we can come back and machine to aerospace levels of finish and quality. Just a brief overview of the steps we go through while we are validating tools or materials for tooling applications. So everything starts with compounding, and then we'll move on to print trials. Post-print trials, we will perform some mechanical screening, tweak things if needed, but then start scaling things up, look at in-depth lab analysis, as well as printing, articles for the intended use. And then we'll start working with other machine manufacturers, validating the materials work on their machines, and continuing to work with customers through fabrication. So compounding is kind of where it all starts, right? As I mentioned, Airtech's been compounding extruding now for 50 years and over 40 years of experience with various other different tooling materials and applications. So really raw materials are selected knowing the intended use. And the goal is to develop resins that are capable of meeting the expectations and really just drive the technology forward, right? So we want to make sure that the materials can keep pace with the development of the industry as a whole. And like I said, push things forward. So after compounding, we come to print trials. So in print trials, we're going to really just leverage the knowledge of what makes things printable, but evaluate everything through the process. So looking at essentially, layer times, looking at the thermal properties, warp, start stops, how those are tuned and tweaked, make sure that it's really meeting our expectations, but also looking at things like step over, printing at angles, bridging, those kinds of things, but really ensure that we are meeting the expectations for the intended use. But to date, we have printed and characterized over 350 different resin formulations, and frankly, we're not sitting on our hands either. There's probably another 50 to 70 that are in the pipeline here. So post-print trials, we'll look at mechanical screening. So really everything is done with the intent of as printed, right? So you can see several of the coupons there. But this is not injection molding. In reality, the injection molding properties really don't do anybody any favors. But we're going to start looking at things like tensile strength and modulus, elongation at break, flexural strength modulus, CTE, as well as glass transition temperature. Again, just making sure that it is meeting the expectations. Post-initial screening, we'll start looking at larger batches. Obviously, we want to make sure that things are scalable, but then we'll also start producing material enough for a complete mechanical analysis, as well as printing demonstration articles and testing them in the intended use. So in general, a lot of the compounding will happen here in Huntington Beach. It then gets transferred to Tennessee, where I work very closely with the team members there. Tools get printed, they come back to Huntington Beach. We have ovens, autoclaves, all the bagging materials that we would need, and we'll start validating them in use. So post the scaling up of compounding, we'll start looking at a more in-depth analysis, right? So this is all third-party testing. It's all that data is available for spec qualification with our customers. But we're looking at all failure modes. And the idea at this point is really to understand the mechanical properties as a function of time. So with 3D printing, there's kind of this Goldilocks zone where things are not too hot, where they can still remain stable. But then you also want to deposit material back in a timely fashion so that we can so that you get good mechanical properties. So really the drive here is to enable stress analysis as a function of layer time. So we can take the slice geometry, look at what the deposition time is going to be, and perform a stress analysis prior to printing. But in conjunction to that, we'll also start doing contact material testing. So we have an extensive database of materials that we've validated to date. That includes solvents and cleaners, seal and release agents, as well as production tooling resin systems. So you can see just a little sample of it there. In general, good, bad, and ugly, we're happy to test it. Sometimes you get surprised. So there's a broad database that is living and growing every day as we work with customers. And frankly, if we haven't tried it, we're happy to try it. We have plenty of flat panels here in Huntington Beach or in Luxembourg, as well as in the UK. Autoclaves are available, so happy to test any resin systems if we haven't. So also look at, like I said, printing demonstration articles. So you can see a few examples there, as well as the actual cycle test tool. We'll cover a bit more of that here in a minute. But in general, no secondary surface coatings are needed. The tools get printed, they get machined, and then they are vacuum tight and autoclave capable. All of our materials are post machining. So we've also done an extensive amount of work with annealing trials, validation, looking at long-term use of the tools in a production type environment. So long-term autoclave cycling, looking at dimensional analysis and the vacuum integrity, as well as, like I said, fabricating parts off of the mold in conjunction to that cycle testing. So as I said, working with all machine manufacturers, so I'll probably cover it a little bit more here in a minute as we go through. But at least these are the folks that I can be transparent about. We are working with a lot of machine manufacturers that are in development. But really the intent in working with other machine manufacturers is validating that our expectations can be met on their machine. So again, showing that the mechanical data that we publish can be achieved on their machine as well. So we'll also help with extrusion, validating the mechanics again, third party, and frankly, just being transparent about those results. So we'll also look at printing test tools. So you can see an example of a tool made on one of the seed platforms. And we'll cover it a bit more in a minute, but as well as the master print system from Ingersoll. But then we'll also work directly with customers. So even using the tools, everything from the bagging materials, the sealant tape, those kinds of things. And then we also keep an ample inventory of materials, both in the US and in Europe. So again, the idea is keeping additive rapid, right? So, and we're happy to work with those that are considering a machine purchase all through the process. Frankly, we want everybody to buy a 3D printing machine. So a little bit about the barriers we're working to overcome in the production process, right? So what are those, right? Lack of mechanical data on the current materials. It's quite common that we've seen to see materials that are made but not tested and validated, right? So again, we want to prove those in use, as well as show some history and help customers understand how to overcome some of the anisotropic properties of the materials. But there's also some misconceptions about the material toughness, what accuracy can be achieved, as well as showing that we can meet the thermal requirements for spec use. So it all starts kind of with the mechanical and functional testing, right? So like I said, this is not injection molding. We really need properties that are as printed. Really, why is that needed? Larger tools, the bigger you get, especially things that start going overhead, we really need to be able to perform a stress analysis, make sure that the tools that are being produced are safe for the end-use customers. And then again, third-party test analysis, and making that data available for qualification. So we've done a significant amount of work with the national labs here in the US, as well as in Europe, validating the as-printed performance. But again, making sure our materials are machine agnostic, that we can work on any print platform. And then understanding how those Z mechanics change as a function of layer time. So typically the bead stacking will drop off as you push the layer times longer and longer. The X values will remain fairly consistent. As you go and print larger and larger, sometimes you don't have a choice, and you need to understand if the tool is going to meet the intended use, if we are pushing that layer time longer and longer. So again, proving them out in use. You can see the cycle test tool that's there. Like I said, we are past 350 autoclave cycles now. We're not seeing any signs of failure. And again, no secondary sealing is needed for that vacuum integrity. We do expect it to go past 500 cycles. We are continuing to cycle that and pull laminates, and then again, publish those results. And then we can also achieve a very nice surface finish, depending on the requirements. So and these are all done prior to any seal and release application. So you can see a 16 micro-inch finish there. So very close to a Class A automotive surface. And we have continued to run some additional trials with polishing to see how good of a surface we can achieve. But Class A surfaces are achievable for automotive applications.
Zach, I have a quick question on the specific slide. What about the hardness of this material? How do they compare to pre-preg or metallic tooling?
So there's a common misconception that we've seen in the industry that the thermoplastic, they're plastic, they're soft, they're not rigid. In reality, we're getting very close to the hardness of aluminum, especially as we move up into the higher temp polymers. And similar to thermoplastics in the aerospace industry for part applications, but the resin matrix itself is much harder than, say, a traditional thermal set. So the tools are much more robust than I would say most people give them credit for.
Okay, and have you done any studies on how good of a surface finish is achievable on tools made with this process?
Yeah, so as a challenge, post actually taking this picture, we asked the folks in Tennessee, and I apologize, I don't have the conversion into metric. Well, I guess never mind. I'll extrapolate it from my spreadsheet there. So we have achieved better than a 0.2 micromillimeter surface. So very, very, polished surface. And that was prior to any seal and release application. So once the seal and release is applied, obviously it'd be even better than that. But like I said, Class A surfaces are absolutely achievable.
Thanks.
So this was off of the cycle test tool. This was post 250 cycles. We are still evaluating it at 350. I can tell you right now the data is identical. But this is just the data post 250. So this is the raw autoclave data, 100 PSI, 355. Benjamin's shuffling around on me. So 100 PSI, 355F, so 185C and 7 bar. But you can see the raw autoclave data. Again, sorry, this is in not in metric units, but vacuum probe 1 dropped about 0.2 inches of mercury, or about 7 millibar. Vacuum probe 2 dropped to, it kind of fluctuated. We'll call it 0. But again, that was, vacuum is shut off at temperature and pressure. So very well within any specs that for vacuum integrity. But we also performed a fiberglass leak check. Folks that aren't familiar with it, it's kind of the gold standard in tooling for knowing where a leak is, right? So that 0.2 inches of mercury that dropped, that 7 millibar, if that was in the tool face, that would be problematic. But you have all these, potential sources like bagging ears, through bag connections, couplings to hoses, couplings to the autoclave. All of those can leak a little bit. So understanding that the tool surface is solid. So we took some 7781 glass, so very thin fiberglass, and then our own Airtech beta resin system, so benzoxazine resin system. Traditionally, they're done with epoxies. We chose to do the benzoxazine just due to the very high gel point. So we wanted to capture as broad of a processing window as possible. And as you can see in the laminate there, there's zero indications of any porosity, excellent surface finish. So the idea is you can hold it up to the light. If you had a leak, there'd be kind of like a starburst pattern coming from where that leak is at.
And Zach, I have also a question on this slide. Are any secondary coatings needed for vacuum integrity in the autoclave?
No. So everything as printed is vacuum integral. We did do, I see a question from Chris Fleet there. We did do multiple pulls through the process to expedite the testing through that 350. We weren't doing a pull every cycle, but in general, we pulled a laminate every 5 cycles. So we would lay up a laminate, run 5 cycles overnight, and then the next day repeat the process.
Okay, thanks.
Again, looking at the long-term dimensional stability. So we do have a very detailed test report that we can provide to customers. Feel free to reach out if you'd like to see it. But this was an overlay post-cycle testing to the original scan data. So no surface deviations greater than 0.005 of an inch. You can see the overlay there. And again, looking at that surface integrity. So like I said, there's kind of some misconceptions on the material toughness, but we have been pulling laminates from that tool. You can see a couple examples there. Benzoxazine and an epoxy down there at the bottom. Obviously, we've tested everything that we have in our inventory. No issues there, but we've also been pulling production resin systems off of tools. just showing that they will work. So that includes BMIs, epoxies, cyanate esters, in the autoclave, out of the autoclave applications. And like I said, if we haven't tested it, we're more than happy to go test it. But you can see just an example of the gloss that can be achieved coming off of the molds. Just a visual of the tool after cycle testing. So you can see there's really no visible deterioration or ever it's any kind of damage or oxidation. So we're currently evaluating the 350 cycles in California and Tennessee locations, again, trying to share that information. Under the microscope, so you can see an example of the tool surface. So we're not really seeing any evidence of micro cracking or surface degradation. So in traditional thermal set systems, the failure mode is typically that micro cracking. That micro cracking leads to delaminations. Ultimately it'll lead to loss of vacuum integrity, but really just seeing no evidence of it whatsoever. So understanding those thermal properties. So, the example here on the left would be kind of an example of a tool that's printed on its side. We'd stand it up, machine the surface there. So understanding how the thermal properties affect the tool itself. Quite often we are choosing to print in either orientation based on the tool geometry. So, not all things are printable, understanding that, where it's a good fit, where it's not. And we're more than willing to help customers understand that, work through that. But in general, we will take a surface, we will compensate it based on the orientation it's going to be printed in, make sure that the tool will be in the right place and during cure. And then, frankly, being transparent if things are not a great fit for the application. So like I said, it's not a solution for everything, but when it has a place, it's a great solution. Again, just proving them out in use. We're also leveraging the global team. So this is actually a tool going into the autoclave in Luxembourg. But the high tolerance of the surfaces are achievable. So, aerospace quality levels of finish are not a problem. We can install precision holes. We can set details in post machining. But we've seen proven results with masters, layup molds, preform tools, holding fixtures. You name it. Even in metal forming applications, we're seeing some great strides. Again, prior to us really endeavoring in this effort, there hadn't even been a lot of, showing what's possible from just a hardware standpoint. So you can see hoist rings are added. You can't see it in this picture, but this tool actually had some bushings under the laminate there. But then, integrated plumbing, those kinds of things, all threaded inserts, edge bars, all casters, all these things can be installed post printing. Also looking at the consumables. So we do have a brochure available of all the materials we've tested, and then our recommended materials to use for the given application. So, everything from the low temp applications all the way up to high temp. We've also done a considerable amount of work on how to design tools to achieve the thermal performance required. So in general, the backup structure, everything, all of that is printed in situ with the tool face sheet being printed. So, but printing in things like large windows and then limiting thermal mass, right? So limiting contact with the face sheet, allowing for good airflow. So, but also, given that it's 3D printing, things that are achievable with traditional processes, but, really cost prohibitive, but, we can do things like print in contoured headers or grow a header to only contact where it's needed. Again, minimizing the heat sinks, allowing for good airflow. And then we've in that process, we've seen vastly improved thermal cycles compared to things like epoxy or urethane foams. In general, they kind of fall between a metal tool and a composite tool in their thermal performance. So quite good performance in general, allowing for really good cycle times through the autoclave. So just in general, kind of a summary, the development process really should not end after compounding and basic mechanics, showing that things will work in use. And frankly, different applications require, diverse offerings. But showing that the properties are predictable and that we can validate them for the process of production tooling. So really showing the results proven in application, being transparent about those, and then securing, long-term process stability, as well as technical support for the 3D printing, helping those that are looking to set up, and then, sharing a demonstration of successful projects. And then again, all materials are readily available in inventory and commercially competitive. So just wanted to share a few examples here, as well as just a brief overview of the tooling process, right? So very similar steps to traditional tooling. Printing is the primary step. So really the magic is all in the printing. Kind of after that, it's business as usual. The only real difference in the process flow is in a traditional tooling approach, you have some float time with the NC programming. The printing happens so fast that you really need to be NC programming from day one, because in general, when we hit go and print, the next day we're machining. So you really don't have much float time there for the NC programming. And just a kind of an overview compared to that traditional process, we're seeing a vastly reduced lead time. So 75, even 80% reduction in lead time. Again, most of that happens up on the front end. So, you see a significant reduction in the touch labor and the fabrication process needed to just get to 5-axis machining with traditional tooling processes. But then, we're also only putting material where it's needed, right? So just some examples. Our primary focus has been in the aerospace tooling market. So trying to share what I can. Obviously, being aerospace, that doesn't happen too often. But this was a spar mold we did for an aerospace customer. So this was 350 cure, 100 PSI, just to give you an idea of what's possible. So that was roughly about 2.5 meters long, 1 meter wide. It was printed in 7.5 hours. But that tool is actually designed, built, finished in 3 weeks. So quite a rapid process in general, just frankly what's possible. But it also led to the successful adoption of 3D printed tools at the customer. So we've printed quite a few larger components for them now too, up to about 3 meters by 3 meters by 1.5 meters. So quite large tools for layup mold applications. This is an example of a kind of a joint venture we did with Ingersoll and their master print system, as well as Camozzi in Italy. And then the part was ultimately fabricated by Plyform Composites, but it's a helicopter door mold. So you can see it was actually a multi-piece tool. It was standing up here on display at JEC, but so the mandrels weren't in there. But you can see the part. But that again was 180C and 7 bar. It was a 3-piece mold design. And this was a lightweight AFP mold that we put together. So this was a 4.3 meters by 2 meters, so quite a large tool. You can't see it in this picture, but there was actually 2 removable mandrels on either side that were printed. There was a metal support frame that would come and grab and flip this thing into the layup mold, but it had to be held in this orientation for the AFP, so the automated fiber placement, but it was actually a 4-piece tool design. So it was used at room temperature and then transferred into a layup mold. But it did include stress analysis and some tip over analysis to ensure it could handle those AFP loads. And at least to our knowledge, this was a very complex programming side. There was over 100 tool paths per half there. So at least to our knowledge, more tool paths than anything else that's been produced with large format additive. Another project that was done on the master print system with Ingersoll, but that was done with our Dahltram i350CF. So this was part of a next-gen fighter development with BAE, as well as the National Composite Center in the UK. But 180C and 7 bar again, so quite a large fairing mold. Another example of some work that's in progress, but this is a out of autoclave application. So this was a large fairing mold that was printed. It's about 1.5 meters by 1.5 meters by 1.5 meters. And that was printed in 6 hours at Airtech Center of Innovation here in Nashville, Tennessee. But it's 400F capable, but we needed access to the backside. So you can see the heater blankets that are bonded on there, as well as integrally stiffened it. So this did have a carrier. You're looking at the backside of the tool there. But we will be using that as a technology demonstrator, producing some test articles and a test report. So stay tuned. We're happy to share more. Another example, so this was actually done on the seed/Bellotti machine, the bead platform, but this was done with our C250CF, so 250 autoclave cure application, just showing the car hood there for Pagani. So this is an ongoing program, really just trying to evaluate the technology. And I do have a little short video we can share right after this, but we did produce some molds for a local company in Huntington Beach, California, BBI Racing. But this was our Dahltram C250CF out of autoclave pre-preg application. So we printed 6 tools. Multiple tools were printed at the same time, so you can leverage some economies of scale there with a large machine. But in general, we will nest tools and print multiples when we can. Help reduce the cost, right? But those were 6 tools. They were designed, printed, delivered in under 4 weeks, and then all of the parts were completed by week 6. And then I won't quite spoil the finish of the video, but Benjamin, if you want to bring that up. So this was a little video that our customer put together for us.
Good ideas die in the valley
just showing
everybody goes through
the benefits
no
that we
I don't care who you
that
are.
we're seeing.
Great idea, conceptually works. All right, mobilize. How do we then get from that great idea to manufacture it to an end result, right? It doesn't matter if you're starting a business, it doesn't matter. There's always these complexities. They design an amazing splitter. Wow, this thing works. Cool. How do we build it? Well, there's 36 pieces to it. Okay, so are we 3D printing parts of it? And then how do we lay up the carbons? Now we got to buy material. We have to make a mold. Well, then, so Dimitri reached out to Airtech. They 3D printed our molds. I mean, so they have a gantry style 3D printer that is, its printing envelope is 10 feet tall, 10 feet wide by 40 feet long. They printed everything out, and on the same platform, tool change, comes in and remachines all the surfaces. And then it cures, and then they re-CMM it, and using Creaform components that ScanHub does also. So
my name is Gregory Hay, and I'm the Director of Additive Manufacturing for Airtech International. Today we're here in our facility in Springfield, Tennessee. This is our new Center of Excellence for large-scale additive manufacturing, or 3D printing. So this is where we offer services and also resins for large-scale printing of tooling for composites. So we serve all markets globally, both here and out of our facility in Luxembourg. And this is really the quickest way we can get you high accuracy, high performing tooling without the wait time and without excessive cost. So this technology is unique that we can go from a printed near net shape to a finished mold in a very short amount of time. And so this is where BBI became interested in our technology, and we found that a really tight timeline really identified a need where we could put a tool in their hands faster than any other technology, but also be able to do it at aerospace levels of quality and finish.
Airtech shrunk that valley of death to almost, it really just came down to nothing. I mean, it was just like, oh, that's a great part. This is the mold we need to make for it, and we're going to print it and cut it and ship it to you and just start laying up the carbon. That was insane. They're just an awesome family-run business. That has been instrumental to us being able to get out of that valley. It's a combined effort with a lot of people, and all of a sudden then things start to happen. You start achieving all the things you think you can achieve. You can't do it on your own.
You are mute, Zach. Yeah.
So yeah, one of the great benefits is, we jumped through all those hurdles. It was quite crazy, but at the end they ended up winning. So all things were worth it. Some of the ongoing development that we're working on. So 3D printing itself is really a great way of reducing the carbon footprint. You're only putting material where it needed. But we wanted to launch a larger design study on what happens to tools at the end of their life, right? So there's a lot of talk in the industry about how thermoplastics can be easily recycled, but really just showing these were actual chunks of tools. You can see headers and stuff like that here. So taking the tools, recycling, but we're going to be performing a much larger program, looking at how to reclaim and reprocess tools that have reached their end of life. So that's really going to include the in-depth mechanics that we already share with customers, but then also printing some demonstration articles with those materials. But also expanding into new applications. We've even performed some metal forming applications. We've seen some really great benefits to the strength of the materials. In general, they're much tougher than some of the higher density urethane or cast urethane type systems. So seeing some great benefits there. The example of a stretch form die that we 3D printed for an OEM. So that was actually quite a fun program. They were taking bets on when the tool was going to fail during the forming process, and it didn't. So we got to make all the old timers eat their lunch. And it's really helped to develop a much larger program with them. But then we're also seeing some metal casting type applications. In general, when you're really getting up to the size of large format, so heavy industrial type applications, we're starting to see some benefits with casting. So feel free to reach out if you have any questions after. I know we got a little bit of time slated here for Q&A.
Thank you very much, Zach, for this great presentation. Indeed, it's now time to open the floor to question, and I see that we already have few in the question tab, so thanks for the people asking question, and really don't be shy, and I'm sure you have question to Zach, so it's time now to ask your question. Let's move with the first question. So in fact we got one in the chat at the beginning from Chris Fleet, who was asking how many pulls have you had of the tool?
So we have been doing pulls, like I said, every about 5 cycles over that thermal cycling process. you know, like the intent was to gather the data in an expedited manner. So we weren't doing polls every time, but we do have multiple customers that are using them in a much longer term environment. So no, like I said, we are going to take it to 500 cycles. We haven't seen any real issues or showstoppers. So we are continuing. And then once that's complete, we will make that data available.
Thank you, Zach. Chris, I hope it answered your question. We have another question from Michael Jacobi, who is asking, have you ever tried annealing between printing and milling? And what is the effect on dimensional stability?
So in general, you know, we have looked at annealing. Is it needed? So all of our materials that we offer at the moment are all amorphous materials. So in general, the consensus in the industry is that amorphous polymers do not need to be annealed. I can tell you that depends. Depends on the tolerance that's needed. Depends on the tool geometry that's being made. But then also depends on how many cycles it's going to be going through. So if it's a low rate, you know, R&D production type environment, you absolutely don't need to anneal. If you're looking at a long-term use tool that's going to be heavily cycled, absolutely recommending annealing cycles or annealing the tool prior to finished machining. So we do have annealing cycles that are available, and then we've been performing a much more longer-term evaluation on annealing currently.
Thank you. Next question is from Chris Owells, who is asking, I understand that CTE is not isotropic by a factor of approximately 10. How do you mitigate this in tool design?
So in general, we will try to print in a way that minimizes any CTE issues. So, you know, if possible, that's not always the case, right? So you do have limitations of 3D printing. They're kind of similar to traditional FDM, you know, desk type, you know, printer limitations. The real difference is with large format, you can't just break off support material. You have to machine it. So when you're printing support material, it very quickly subtracts from the value proposition. So there are limitations in which orientation we will print it in, but to answer the question more pointedly, we will compensate the surface prior to printing. So understanding which orientation it's going to be printed in, compensating for each of those axes independently, and then printing the tool knowing that it will be at the proper location at cure temp.
Thank you. The next question is from Ratan Singh, who is asking, does Airtech has a presence in India?
Yes, we do provide materials to India. We do not currently have a facility in India, but we do ship all of our materials there. So feel free to reach out if you're looking for anything. Happy to help.
Yeah, again, you have Zach contact details on screen, so don't hesitate to reach out to him directly. Next question is from Jan Gent, who is asking, all of your examples have shown mold tools for pre-preg materials. Have you evaluated this technology for liquid composite molding and RTM?
Yeah, not a problem. Easily achievable. So, you know, we have looked at closed mold applications, you know, well, you saw some examples of multi-piece molds, but closed molds for liquid transfer molding, not an issue. You know, they're autoclave capable and vacuum integrity is easily achieved. So kind of all things are possible.
Next question, another question from Chris Owells, who is asking what level of benching is required after machining compared to an epoxy pattern?
I would say benching is very similar to a machined thermal set tool. And I'm assuming he's talking a composite material, not just a epoxy foam mold. So it would be, like I said, similar to a machined thermal set composite tool. A little bit harder to abrade than say a foam.
Thank you. Next question from Christian Gonzalez, who's first is thanking you for this webinar and the info you are sharing. Thank you, Christian. His question is the printed material releasable, meaning you lay up the material without the use of release agent, or you still have to use releaser?
No, you still need to use a release agent or a barrier film. So the materials themselves will take epoxy, for example. Epoxy bonds really well to all the print materials. So no, they are not releasable just as printed.
Thank you. The next question is from Anek Nudelman. Have you tested the behavior of 3D molds in thermoforming, hot press, manufacturing process?
So we have done some studies with a few customers looking at these types of applications. In general, for those types of molds, they are they're typically with aluminum. No, we don't have aluminum's conductive properties, but we have validated them for lower rate R&D type programs.
Thank you. We have another question from Stefan Treina, who is asking, is Airtech looking into LFAM with liquid resins, processes such as inkjet or SLA of interest to achieve different properties?
I guess I'll say maybe. We're always looking.
Thank you. If you have any question from Zach, it's time to ask them. We still have 5 minutes. I have some question on my side that I would like to ask you, Zach. How many parts can you produce with one mold? Like we're trying to show with the cycle testing that longer term use is easily achievable. Trying to show just 500 cycles, but more is definitely achievable. It's really going to depend on the tool design and the end use application. How the tool is being treated, how it's being abused, in that shop environment. Okay, we received 2 new questions from the audience. The first one is from Jan Gent, asking, you have highlighted the sustainable nature of LFAM tooling. How will you work with customers to achieve your sustainability goal? Buy back tools from customers, etc.?
Yeah, so we are evaluating that business case at the moment, but more importantly, trying to show that it will work first. It very likely could involve buying back tools from customers. Really just need to look at the economics of the whole situation.
The second question came from Chris Fleet again. Thank you for all your question, Chris. How easy is to repair the tool surface if damaged post-machining at the customer site?
So we've done a broad amount of repair testing that we'd be willing to share, but a lot of the traditional products used, is something as simple as a fill and fare. That can easily be achieved. We have validated all the Airtech tooling repair materials, as well as launched a few unique ones. But we've also looked at things like thermoplastic welding, those kinds of things. I'm usually pretty hesitant to recommend thermoplastic welding to customers. It's kind of a foreign art to most in the aerospace industry. But we do have tooling repair materials that are available, and we'd be happy to walk you through them.
Another question from Chris Owls. Do you machine in the same orientation as you print?
Depends. So depends on how it's printed, depends on, intolerances, those kinds of things. We could easily machine in the same orientation, but depending on how the tool is printed, we will kind of surface all of the sides. So in general, it is does involve some different setups, but it is possible to machine in the same orientation.
Thanks, Zach. We have no more questions and we are running out of time. So we have now come to the end of this webinar. I want to thank you everyone for joining us and thanks for your questions. Again, don't hesitate to get in touch with Zach if you have any more questions. You have his details on screen. We hope, as usual, that you enjoyed the time with us and have discovered a great technology today. I also want to thank Dak and all people involved at Airtech for this webinar today. Thank you very much. And if you are attending GEC World in a few weeks now, you can meet with Airtech Advanced Material. They will be exhibiting on 2 booths. The first one dedicated to Airtech large-scale 3D printing in Hall 5, E32 for the location. And the second one in G39, so really close to the first one. And this booth is dedicated to Airtech Advanced Material Group for vacuum bagging materials and composite tooling. Again, thank you very much. And I forgot to mention that Airtech will be also featuring a part on the Innovation Planet dedicated to mobility in Hall 6. So don't hesitate to pass by if you want to see one of the parts made by Airtech. And I think it's the one of that we talked about BBI Autosport. Again, the webinar was recorded and the link will be sent to you right now together with a link to download Zach's presentation. And the webinar will be also available on GEC Group Web TV at gecomposites.tv, where you can access to all previous webinars and exclusive video contents, conferences, etc. Thank you again very much. We look forward to welcoming you all at GEC World 2022. After 2 years of pandemic, we will be really pleased to see you again at the show. So thank you very much, and really I hope to see you all again soon.
Yeah, thanks everyone for attending. Thanks Benjamin, and come see us at GEC World.
Thank you, Zach.
Thanks, guys.
Bye-bye.